All right, folks, these are the answers to 1977, number 2. And this is so old, I don't have the average for it. I don't have the point value, but it's still a good, really good practice with, it's actually not, it's kind of slip first, and then they reference no slip. But so this one's tricky, and I wish I did have the average, but let's just get started. So you have a uniform cylinder of mass m and radius r. It's at rest on a rough horizontal surface. So again, not slipping requires the surfaces to be rough enough so that wheel can, as it rolls, the nooks and crannies lock into the nooks and crannies below them and then lift off. Okay, so rough means you have the potential for static friction, which is good. That's what you want for no slip. But clearly, since I told you in advance, this is going to slip, and then we're going to have sliding friction and energy loss. Okay, and then they give you the rotational inertia of a cylinder. Sometimes they do, sometimes they don't. And then you have a string is pulled upwards. So think of this like similar to the toilet paper lab, which you've done before, where that string had tension. And the tension, they give you the magnitude in terms of the weight, so things will cancel. So they tell you what that's equal to. And whose direction is maintained vertically upward. As a consequence, it accelerates horizontally, which might seem weird because the net force is up. So again, that's the first kind of like head scratcher there. So it is accelerating horizontally. Let's think about that. Here is your pivot. This is creating a torque to make this go clockwise. And if it does that, then the nooks and crannies are going to try to slide to the left relative to the surface, which is going to cause the nooks and crannies to kick back, causing a frictional force here. So there is a horizontal force, which is causing horizontal acceleration. So I kind of jumped ahead, but again, that just reading that through, I'm like, wow, how does that happen? They're talking about a vertical force, and it's saying it stays vertical, and then all of a sudden, oops, we've got horizontal motion. How does that happen? So that is not a typo. It has horizontal motion because it is slipping. Okay. And then they give you the coefficient of kinetic friction. Mu is 1/2. And remember, and mu does not have units. Okay. So, question A. On the diagram below, identify and label each force acting on the cylinder. Draw each force from its point of origin. Whenever you see that from its point of origin, that is a hint that you're going to be needing torque. Because if you're not doing torque, then it doesn't really matter where the force is. But if you are doing torque, where the force is acting, it determines your lever arm R. So that is a big fat hint. All right, so let's go through. We must never forget this. The cylinder has weight. And again, we're trying to do force of weight. There's no mechanical force. There is a normal force. Point of origin is the ground. That normal force is not equal to the weight because we have additional vertical forces. Oops, sorry, I should call that F subnormal. There is friction. And again, I think the direction of friction is really, really tricky. So since that force is pulling up, it's trying to make it rotate this way. So that means these, without friction, this wheel would just spin around and around and around. But you can see these, the edge of this disc is trying to go this way relative to the surface below it. It's going to catch on the nooks and crannies below, and that's going to cause In this case, they said kinetic friction to the right. And the point of contact is the point of contact with the ground. So this is the force of kinetic friction. And there is tension, and they told you what the tension was. It was 3/5 mg. Okay, so the hardest part there was the direction of friction. Hopefully you got everything else, but don't be lazy. Be really careful about where you draw those forces. Make sure you draw arrows at the end of each force, or you will lose points. But that, in theory, would be maybe 3, maybe 4 points, like a point for each force. Okay. Question B says determine the normal force. So that is in your vertical column. That's easy, I hope, because we know that there is no vertical motion, and that's, hopefully you can see that, because 3/5 g is less than 3/5 mg is less than mg, right? So it's not enough to lift it off the surface. So you probably get a point for saying the forces are balanced, and then you have, the force of tension plus the force of the normal minus the force of the weight, and nobody's winning. And they told you the force of the tension was 3/5 mg. We're looking for the force of the normal, and the force of the weight is 1 mg. And so 3/5 mg minus mg is 2/5 mg. So the normal force is 2/5 mg. And in part, I think they're trying to give people something to, like a doable part of the problem. And I'm sorry, I'm looking at my answer key. Okay. I think that's it. I think that let's see, right. Does it say, you don't have any numbers, so usually they say write all answers in terms of the given quantities. Maybe I didn't copy that when I digitized this. Okay. Determine the linear acceleration A of the center of mass. All right, so when they say center of mass, that is a hint. You're going to revisit your force diagram, and if it helps you to redraw it, the center of mass is like, I don't care about the point of contact. So the tension is up, the normal is up, the weight is down. We kind of already dealt with all of these. Sorry, I'm not using the same convention, but you get this. So we already dealt with all of those forces, and we have friction. That is the only horizontal force. So that frictional force is what's causing the acceleration of the center of mass. So, and for those of you who, sorry, I'm just going to, I know there was one class in 2025 that didn't do the spool demo, but I don't think you have anything you could try. You could try this with a roll of toilet paper or a roll of paper towels at home. Even though you're lifting up, by making this turn, what this thing is going to do is roll this way as you lift up. I will point you to a video clip of this in the original PDF or Google Doc. Okay. And okay, so linear acceleration means I'm going to go to my linear column horizontally, and I'm going to say the sum of the forces is not balanced, but is equal to MA. Okay, and then I only have friction, so yay, that's easy, apparently. Looks equals MA, and that's what I'm looking for. And friction equals fun. And that's why they had you find the normal force, which was 2/5 mg. And then you realize, nice, that the m cancels. So the acceleration is mu times 2/5 g. And they gave you that mu was a half up at the top. So yay, the 2's cancel. And so the acceleration is g over 5. And that's one of the nice things about not having numbers is you can see, okay, g is already in units of meters per second squared. I'm going to divide by 5. So you have the right units, right? Whereas if you had ended up with acceleration is like g squared over 5, clearly that's wrong because they don't have the right units, or g times m over 5, that means you canceled one m but not the other. So using variables is a great way. Now this doesn't mean you have it right, but it's a somewhat of a good check, like that it's not wrong, if that makes sense. You know you have the right units. So it's accelerating at whatever 9.8 over 5 is horizontally, which seems weird, but remember the frog demo where the frog went across the room? Friction, and it is sliding friction, but occasionally in some weird circumstances, friction can make things, that's the only force. The nooks and crannies are bumping it to the right, and it is moving to the right, instead of bumping on it as it slides across the surface and slows down. Okay. D, calculate the angular acceleration. So that hopefully is a big fat hint that, again, every time you have a force diagram and they say point of contact, that means you're going to do F equals ma and torque equals I alpha. High probability. Okay. Calculate the angular acceleration, sum of the torque equals I alpha. I imagine that some people were like, this is easy. I'm going to speed through this. A equals alpha R. I have A, I have R, boom, done. But when you get to question E, you would find, oops, that relationship does not hold. So you just want to be careful. So we'll talk about that in a minute. Okay, so calculate the angular acceleration alpha of the cylinder. Please say sum of the torque equals I alpha. That's worth a point. And then we're going to calculate all of the torques. And they said that I was mr squared over 2. And we're looking for alpha, so we're going to leave that. So let's go back to our force diagram here. The weight is acting on the pivot, so it doesn't cause any torque. The normal force is passing through the pivot. So here's your R. Here's your normal. Going from R to N, let's go this way so it's positive, is 180. The torque is going to be R times the normal sine of 180, which is 0, right? That's just pushing on the pivot. That's not going to cause torque. But we have, let's see we have the tension, which is causing torque, and we have friction, which is causing torque. Okay, so we're going to have 2 torques here. I'm going to do the hands of the clock here so that we can reference the diagram. Okay, so remember R is a vector pointing from the pivot to the force. So we're going to draw that over here. And then we're going to move the tension vector so that they start at the same point so you can see how they are related to each other. And torque is a rough, so you're going from R to F, and that's clockwise, so that's a negative 90. And then vector pointing from R to friction is down, and friction is pointing to the right, and going from R to F is counterclockwise, so that's positive 90. I'm pausing because it is, we know tension's bigger than friction. We know this is winning. And, well, anyway, let's just, there's going to be a minus sign goofiness, but we'll deal with that later. Okay, so we have two torques. So R is easy because both of the forces are acting at the edge, so R is just the radius. F for the tension is 3/5 mg. Is it, or is it 2/5? No, it's 3/5. And that is sine of negative 90 because it's clockwise, plus R times friction. So let's go to our miscellaneous column, and mu is 1/2, and the normal force is 2/5. So friction is 1/5 of the weight. Sine of positive 90 equals mr squared over 2 alpha, and we're looking for alpha. All right, so the good news is m cancels. It's in every single term. One of the r's cancel. So that gives us 3/5 g, but negative, plus 1/5 g equals alpha r over 2. And then g over 5 minus 3/5 g is minus 2/5 g. And again, we care about alpha, so alpha is going to be minus 4/5 g over r. And let's check the units really quick. G is going to be meters per second squared divided by r in meters is going to give you nothing, because remember radians is dimensionless, per second squared. Okay, so that looks good. And it's negative because it is rotating this way. Hopefully that makes sense. It's got to rotate this way to roll to the right. Okay, I'm going to check my work with my key. Okay, awesome. And then your result should show that A and alpha are not equal. So let me just explain. If it was not slipping, then A, no slip, would be alpha times R, which would be minus 4/5 g over r times r, which would be minus 4/5 g. And the reason I was pausing before is A is to the right, so it's positive. And that's why we kind of do winning minus losing, is because A is actually negative alpha r. I'll be quick because this is not going to help you do the problems. But it's rotating clockwise, but it's translating to the right. And so we should have defined this as positive and this as negative, so that A equals alpha r, which would have changed the signs of these. But I'm not going to come in and see me if you need to talk about that, but we're just going to look at magnitudes here. So if it was not slipping, it would have been accelerating at 4/5 g, and the acceleration we got was not that at all, was g over 5. So they're basically saying those two things are not equal. Why is that? Like, explain why that makes sense. Okay, so this is pretty tricky, and even as I wrote it down, I'm like, it's hard to imagine this. So you probably would be fine to just explain that since it's slipping, that relationship does not have to be true. Not clear because it's such an old AP, but I will try to explain how this works. So in order to not slip, that point of contact needs to be 0. So the no slip condition of V equals omega R means that the wheel is moving forward in space. It's translating through space with a speed V and rotating with a speed omega in sync, so that the speed that this purple dot has from being a distance r away from the pivot is exactly what it needs to be to cancel the forward motion. So if you remember, you're on the merry-go-round on the cruise ship. So the speed of this orange dot is twice the speed of the center of mass, because the cruise ship is taking them moving them forward, and because they're on something that's rotating, that's also carrying them forward at that point. But the speed of the point right here is being moved forward because it's on the cruise ship, but moving backwards because it's on the merry-go-round. And if the speed that it has caused by being on the merry-go-round, that's what this formula is, the speed that the merry-go-round pulls it backwards is exactly equal to the speed that it is going forwards, then that point is at rest and the nooks and crannies can interlock. Okay, that's just a quick review of no slip. So similarly, you can just say, all right, if that's true, then the derivative of that means A equals alpha R. Okay, so the acceleration of the center of mass is, we found, g over 5. And so the disk is moving everything forward at g over 5. Okay, so it's on the cruise ship accelerating faster and faster and faster at g over 5. But it is also rotating, and the rotational speed is speeding up at a rate of alpha. So this orange point right here is doing two things. It's being sped up to the right with a rate of g over 5, but sped up backwards with a rate of alpha r. And because it's rotating faster and faster and faster, which means that every point on it has to move through space in a circle faster and faster and faster at this rate. Okay, so that point of the disk is being caused to move faster backwards because it's on something that's rotating, like the meter stick with the pennies on the meter stick, right? The meter stick was falling faster than 9.8, and that's the formula you figure out to figure out how fast the linear acceleration is, because it's being forced to move through space in a circle. So if you take g over 5 minus 4/5 g, then you get that point is moving backwards faster and faster and faster at 3/5 g, which might seem weird because you know the whole thing is going to the right, but that's just one single point is moving to the left faster. I don't know if I said right. This is moving this one point is moving to the left faster, but it's just a single point. And the acceleration of the center mass represents the aggregate speed of all the points. And remember, this top part gets that additive effect of I'm moving to the right faster and faster because I'm on a rotating thing, and I'm moving to the right faster and faster because the whole thing is being pushed to the right. So this higher to the right speed and all of the higher to the right speeds are going to average out with some of these higher to the left speeds, and not average out, dominate. And on average, all of the particles are accelerating to the right at g over 5. Okay, so again, I think that's really weird to think about this one point moving to the left faster and faster and faster when you know the whole thing is going to the right faster and faster. But hopefully that makes you realize, oh, that's why it's rotating, because this point has to go faster to make it around to catch up with the whole disk, which is sliding, which is accelerating to the right. Okay, and that also should make sense, because otherwise, if this point weren't moving to the left, then we would not have friction to the right. Okay, so that's really, I had to really think about that, you know, and I've been thinking about motion for years and years and years. So that is the tricky part. So don't freak out too much. The moral of the story is be really confident with analyzing an object using F equals ma. In this case, we did it vertically, horizontally, and then torque equals I alpha. Okay, so hopefully that problem went well, and reach out with questions.